Okay, so I graded your midterm exams and posted the grades online. You guys probably saw that. I returned I gave the exams over to the TA to return in section. So if you went to section, you would have picked up your exam. If you skipped section, then you probably did not get your exam back. So, so that's what's going on. And if you have any questions or whatnot, I do have office hours today at after class. Well, first I probably can run to Ackerman and just grab a snack, and then also on Thursday, and I'm happy to answer your questions about the exam or the homework. How's the homework going? Going okay? You guys have making progress there? Okay, and regarding the exam, I tried to do a calculation that was, overall friendly to the most of the class. So the average is around 83, something around there, and then we had about 8 or 9 students score over 100, and then and the distribution was pretty symmetric. So so that's, I think, generally a good sign. And if you did not score super great on the midterm, it's okay. I don't want you to feel like all hope is lost. Okay, it is just a single test, and it is not the end-all determinant of your final grade in this course. And to remind you and put things into perspective is that your academic performance in this class or any class does not say anything about who you are as a person. It does not determine your value as a person. It's the exam covered a bit more syntax and kind of programmatic features of R, and I think those are worthy topics to test on, but no one can tell you that your value as a person or human is any less because you did not score well on such an exam. So anyway, just always want to remind you that your academics have little bearing on your value. So, but yeah, if you have any questions, or if you come by office hours, well, I'm happy to try to address them. Okay. Any comments or questions before we get started? We're all good? Okay, I hope you guys had a good weekend. It's already the end of August, and we just have like this, we're already, past the halfway point in this class. It's going quickly. Okay, so this is the point in the course where we take a little bit of a thematic shift. Okay, so the first half up through the midterm, it was all focused on doing stuff with R. We went into, programming things, functions, learning about features and structures in the R language. Also, using some of its packages, dplyr and whatnot. Now we are going to take a shift and cover some more, I guess, the statistical computing side. Okay, and I kind of alluded to this on our first day of the course, where we said computational statistics is the idea of using the computer and doing these computationally intensive methods to try to answer questions that perhaps are too difficult to answer analytically. Okay, so use the computing power allows us to answer certain questions that are too hard to answer the traditional way. Okay, and before we can get into some of those methods, we first have to understand how numbers work on the computer. Okay, and so I'm going to cover how floating point numbers are stored in the computer, and yeah, you know, maybe I'll just briefly cover this concept of computational time, but that's less important for today's lesson. And then, and after I cover floating point precision, then I'll get into our kind of our first set of numerical methods, which is focused on root finding. Okay, root finding meaning where the equation is equal to 0. And so, so let's talk about floating point precision. Okay. So, okay. When we got into R and we learned about the numbers, how R stores numbers, how does R store numbers? What's the type, data type that it uses? It's called double, okay? And that's that comes from this concept of a double precision floating point number, right? So we have integers and then we have type double, okay? And so, you know, at the inside the computer, it's just bits, right? You got zeros and ones, and using those zeros and ones, we are trying to store numbers, okay? And it's the way we store numbers in the computer is very different from the way we learn about real numbers in math class, right? And so here, let me, before we even get there, I just want to kind of do one. Just a very simple demonstration, right? So if I said, you know, in math, if I said, what is 10 over 3 equal to, and I said, represent this in decimal form, you would say this would be something like 3.33333 ... right? Or you might, mathematically, we can write something like this, and we understand what this means, okay? However, if we think about what this ... means, this means, you know, to infinity, right? There's an infinite number of trailing threes, okay? And we can represent that with this bar over the 3, but, you know, in a computer, we do not have infinite space to write down every single trailing decimal, right? You know, if we wanted to write the number pi, we can just write pi, but the computer can't store all the infinite number of decimals, decimal places, okay? So this, so, you know, let's pretend that the computer can only hold 4 decimal places, okay? Okay, and so, you know, then 10 over 3 becomes 3.3333, okay? And we might have to say this, this becomes this, okay? And then, if somebody says, okay, what if I take this and I multiply it by 3? What are we going to get? We are going to get 9.9999. And then we ask the question, is 9.9999 equal to 10? And what's the answer there? The answer is no, right? This would be false, okay? And so in floating point math, basically 10 over 3 times 3 does not equal 10, okay? Because right here, you know, we lose some information. And there's no real way around this intrinsic problem, okay? We can have more decimal, you know, there used to be single point precision, which had a certain number of basically decimal place representations after the spot or binary positions. And we can increase that to double precision, but the intrinsic problem is that a computer can only represent a finite number of places after the decimal, okay? And if you're forced to have only a finite number of places after the decimal, you are going to run into problems, okay? If you're you'll run into problems if you expect the operators of real math to hold up in floating point math, okay? So, you know, floating point numbers is not the same as real numbers. And this is something we have to get used to, because all through our lives, we've been dealing with real numbers, okay? And we learn things like you can multiply the numbers in any order and it doesn't matter. You can add the numbers or subtract the numbers. I mean, you can add the numbers in any order. You can group the numbers and things like that, right? You learn all of these distributive properties and all of these things that are true for real numbers, but they no longer work for floating point numbers, right? Because technically, in real math, 10 times 1/3 times 3 should be the same thing as 1/3 times 3 times 10, right? They should be the same, but this is going to give a different result from this with floating point math, because the 1/3 times the 3, that will return the number 1, and 1 times 10 will give us 10. But 10 times 1/3 will give us 3.333, which gets truncated with the finite number of decimal places, and then when we multiply it by 3, we're going to get 9.9999, okay? So these are things that we have to be aware of, okay? And this is kind of the big picture concept. We're going to get into a little bit of the nitty-gritty of how numbers are stored in the computer in binary form, but this is our big picture idea for this section of the lesson. Okay, so yeah, machine representation of numbers. Everything is stored as bits with 1s and 0s, 1 being on and 0 being off. And then if you have 8 bits together, that's called a byte. All right, and so we can talk about integers. Okay, integers, we just use the bits, and it's just like representing numbers in binary form. And you probably learned this at some point in your math when you learned about different bases. Okay, and but we have a few different methods for representing integer numbers. Okay, because in you know, in binary arithmetic and whatnot, you know, you have, when it comes to the integers, you have positive and negative numbers, okay? And so we have a few different ways on how should we represent those negative numbers, okay? And those are called sign and magnitude, the biased form, and the two's complement schema, okay? The way integers are stored on your computer happens at a fundamental level, and R has no control over it, okay? Now that everybody's using Intel chips, it kind of is the same. It's like implemented. So, you know, Apple and PC, we both use kind of these Intel-based chips, and so the way the numbers are stored is pretty much the same for everybody, okay? But it used to be that if you had a different chipset from someone else, that the other chipset manufacturers may have chosen to implement the way numbers are stored slightly different from another chipset manufacturer. And so, you know, that we've developed standards across the board to try to get things to go, but these were kind of the ideas, okay? So the sign and magnitude scheme is probably the easiest to understand, but this is not how we really do it, okay? So with sign and magnitude, one of the bits represents positive or negative, okay? And we would represent, you know, so one of the bits is plus or minus, and then the other 7 bits in a byte are used to represent the number, okay? And so if we have 8 bits, okay, we can say the first bit represents the sign, and then the other 7 gets represented, and so this thing would be, you know, 2 to the 5th, 2 to the 2nd, 2 to the 0, and this adds up to 37, and then with the first bit being doing a negative, plus or, you know, 0 or 1, however it's chosen to be represented, that would be negative 37, okay? And so the largest number we can do would be 1111111, which would be 127, or negative 127, okay? And we have a total of 256 numbers that can be represented. The only disadvantage is that we have 2 representations of 0, okay? So we got a positive 0 and a negative 0, and those, you know, if you ask the computer, are they the same? Only if the language understands that plus and minus 0 are the same, that they would understand that, okay? Biased scheme is probably a little bit more commonly used, okay? And basically, you say, okay, if we're going to use 8 bits, we got 256, okay, did I do this right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, and you just say, okay, how much greater is it than this this value? I think maybe this should be negative 127. Yeah, okay, I think I might have done this wrong, okay? But basically, you just shift the starting point to be, you know, halfway down. So with 8 bits, you can have 256 numbers, okay? And then you basically just shift the starting point to be like negative 127, so that at the halfway point it's 0, and then it goes up to 128. So it goes from negative 127 to positive 128, and that would be the case here. Okay, sorry, I made a mistake here. This should be negative 127. And we would have a total of 256 values. So again, so this is the biased scheme here. Okay, so this should be negative 2 to the 7 minus 1. So yeah, negative 127. I apologize. I'll have to fix that. So in your notes, right, this should be negative 127, not negative 255. Okay. And then in the complement scheme, so here maybe I'll okay, so with biased, you know, kind of your minimum value is 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, and this corresponds to negative 127, and then it goes all the way to 1, 1, 1, 1, 1, 1, and this will be 128. Okay, and then with the 2's complement, basically, we look at this first number, 1, 2, 3, 4, 5, 6, 7, 8, and this starts off at 0, and then it goes all the way up to 5, 6, 7, and this will be 127, and then as soon as we get to here, okay, these become they become negative numbers, okay, all the way up to so negative 1 is 2 to the 128 minus 1. So this becomes, what we have over here is this becomes negative 128, and this becomes negative 1. Okay, so it's just kind of like, as far as the binary counting goes, these are represented, quote, the regular way as far as binary numbers go. And then the negative numbers are represented in, I don't know, like this. This is called the 2's complement scheme. Okay, and so you still have the a total of 256 numbers that can be represented. Instead, it goes from negative 128 to positive 127, and it's just that we've kind of remapped the sequence, right? We have a total sequence of 256 values starting at 0, 0, 0, 0 all the way up to 1, 1, 1, 1, 1, 1, 1, except and with 2's complement it goes like this, and then the negative values are represented over here. Okay. Does that kind of make sense? What's going on here? All right, so that's the 2's complement and the biased scheme, and this is how integers are represented. Okay, and I believe in R we don't use 8 bits. We use I want to say 32 bits to represent integers. And we can ask dot machine, what is it, dot machine integer max, $ integer max. So what is that? Is that 2 raised to the 32 minus 1? It's 2 to the, I'm sorry, 2 to the 31 minus 1, yeah. Okay, so yeah, using 31 bits to get to our max, and then that last bit is for the plus and minus sign. Okay. So that's yeah, we use 32 bits in R for integers. So this is the largest integer that we can represent. Okay. Okay. Let's talk about real numbers, okay, or you know, floating point numbers with decimals, right? So with decimal numbers, you know, we can represent things in scientific notation, okay, and that's basically how floating point floating point numbers are represented in the computer. And so, you know, a number like 1200 is 1.2 times 10 to the 3. We do the same thing, except we do it in binary, okay? So we start off with a binary, you know, a number, 0 or a 1, with a dot, a binary point, okay? Not a decimal point, but a binary point, and then, you know, things trailing that multiplied by not 10 to the third, but 2 to the some power, okay? And then, so the first place behind the binary point would be the halves place, and then the second point there would be the quarter, 1/4 place, and then, you know, the 1/8 place, so on and so forth. Okay. And in double precision, we use 8 bytes to store this. 52 bits are used for what we call the mantissa. 11 bits are for the exponent, and then the other bit is for the sign. Okay. You know what? I have all of this kind of like detailed out here. I think it makes more sense for me to kind of write this out here. Okay. So let's just get a little bit of practice putting things into binary. Okay. So if I have this number in binary, okay, what is this in decimal? we would have, okay, so I've got, what is this? This is 1 times 2 to the 2 plus 1 times 2 to the 0 plus 1 times 2 to the negative 1 plus 1 times 2 to the negative 2, right? So this is 4 plus 1 plus a half plus 1/4. Is that okay? And I get 5.75. Is that okay with everybody? So this is 1.011 is 5.75. Just want to make sure everyone's okay. So, because I'm going to keep going here, all right? And so this is how we might represent a number in binary. But again, what we want to do is we want to do this kind of in scientific notation, right? So now we've got like binary scientific notation. So in scientific notation, we only have one spot ahead of the dot, or the binary point in this case. So now I've got 1, so I'm going to just move this over 2 spots. So I have this, and then what would I do? I would say this is multiplied by 2 to the, I moved the dot over 2 spaces, right? Okay, so you know we moved the dot 2 places, so we multiply by basically 2 to the 2, except we have to represent this in binary, so we have 2 to the 10 to represent that we've moved the dot over 2 places. Okay, so maybe I'll write this like this to show that that's a binary 2. Okay, so this is binary 2. Okay, and so what is this? This is technically now 1 plus, not 1/2, but 1/4 plus 1/8 plus 1/16. All right? And so I think this is 1 plus 0.25 plus 0.125 plus 0.0625 times 2 to the 2. And what is this? This is 1.4375 times 4. And if we do the math there, 1.4375 times 4 is indeed 5.75. Okay, so we're representing the same number. First, we started off with in binary form, and now we have binary scientific notation. Okay. And so what we're going to try to do is, now that we have kind of a little bit of an idea of how binary scientific notation works, we're going to use binary scientific notation to represent numbers in the computer. Okay, so the computer uses binary scientific notation to represent pretty much all of its numbers. Okay, so now I need to translate this 1.0111 times 2 to the 10 into something that the computer is going to use. Okay, are we okay with this binary scientific notation stuff? Yeah. Okay. All right. So in the actual computer, in double precision, okay, and double precision, we have 1 bit for the sign how many? 11 bits for the mantissa, and I think 52. 1 bit for the sine, 11 bits for the, 11 bits for the exponent, and 52 bits for the mantissa. Okay, we're going to have like, we'll call this a mini float, okay? So for an educational mini float. And in this case, it's the same structure, except just to keep everything, our lives easy, we will have 1 bit for the sine, 3 bits for the exponent, and 4 bits for the mantissa. Okay, and so I will represent this by going 1, space, space, space. Okay. And so 5.75 in decimal became 1.0111 times 2 to the 10 in basically binary scientific. Okay, and so what we will do is we're going to put this into our thing. So we're going to put a 0 here for positive. Okay, so for the sine bit, 0 is positive and 1 is negative. Okay, and then we're going to take the 4 numbers after the binary point, after the dot. We're going to put these over here. Okay, this is called the either the significand or the mantissa. Okay, and what this, one of the specifications of this number system is that we're always going to assume that this first bit is always a 1. Okay, we're always, and the spot of before the dot is always going to be a 1, right? Because if it was a 0, we would just shift things over some more to make sure that in binary scientific, right? Like when you put things in scientific notation, you shouldn't have a 0 before the binary point, right? Okay. So we always assume the value in front of the dot is a 1 because it is in scientific notation. Okay, and then now what we're going to do for the exponent, okay, it's not as simple as just putting in 1, 0. We're going to use the biased scheme to represent basically 2. Okay, or to represent, we'll say 2 to the 10. Okay, and that part will go in here. Okay, and so we'll I will explain this in just a moment here. Okay, so what we have so far is we've got the positive and then the 0, 1, 1, 1, that goes right here. Okay, so the biased scheme, we're going to use the biased scheme. For the exponent. Okay, and so we have 3 bits for the exponent. Okay, which means we can represent a total of 8 values. We can represent a total of 8 values. And with the biased scheme, the bias is equal to 2 times basically the number of bits minus 1 minus 1. Okay? So our bias here is going to be 2 to the 3 minus 1 minus 1. So I've got 2 squared minus 1. I've got a bias of 3. Okay? And so what we have is 0, 0, 0 becomes negative 3. 0, 0, 1 becomes negative 2. And so on and so forth. Okay, and these are the 8 values I can represent for my exponent in the biased scheme. Okay. All right, and so what we wanted was basically 2 to the 2, okay, or 2 to the 1, 0, and that becomes 1, 0, 1. Okay. So we have to do this for our value. Okay. So what we have is 5.75, which is equal to 1.0111 times 2 to the 10, or 2 to the 2. This is going to become you know 0, and then to get the 2 we have 101, and then 0, 1, 1, 1. Okay, and this is how we would store the value 5.75 in kind of our floating point representation using 1s and 0s. Okay, this is to get this is the mantissa. This is the exponent, and this is the sign. Are there any questions on this? Okay, let me try giving you a like a practice problem. Okay. Okay, so let's see if you can go from binary to decimal. Okay, so your number that I'm going to give you . Okay, see if you can tell me what number this is in decimal form. Or should I just do this? You guys are just kind of staring blankly at the screen. Okay. All right. Well, first of all, what is the sign? Okay, so the sign is positive. Great. All right. And what is the number that we have? We're going to have 1.0010, right? This is kind of what we have. And we have to know this is going to be 2 times some value here. Okay? So what is 010 in terms of the exponent? Okay? So 010 in the biased scheme. Okay? Well, 010 is 2, right? And what is our bias? Our bias is basically a -3. So we would take this and we would subtract 3 from it. And so 010 in biased scheme will be equal to -1. Okay? So here I've got 1.0010 times 2 to the -1. Right? So this is going to be 1 plus, and this is the halves, fourths, and eighths place, right? 1 plus 1/8 times 2 to the -1, which is 1/2. Okay? All right, and so now I've got 1.125 times 0.5, and this gives me 0.5625. Okay, in floating point, we have 2 values are reserved for positive infinity and negative infinity, okay? Okay, and that's when all the values in the exponent are 1, and all values, or I'll say all bits in the mantissa are 0. Okay, so so what we have is, so you have 0, 1, 1, 1, 0, 0, 0, 0. This becomes positive infinity. And then if you have a 1, 1, 1, 1, 0, 0, 0, 0. This is negative infinity. Okay, and if you have anything other than all zeros, then that becomes not a number. So if you have 1, 1, 1, and then let's say you throw in something other than all zeros here, this becomes not a number. Okay, so in your computer, when it says something like not a number, this is represented this way. Okay, just something other than all zeros in the mantissa. This returns as not a number. Okay, so an implication of this is that the largest exponent that's allowed is going to be 110, right? So technically, so the largest exponent allowed that is not infinity, okay, that will not give infinity is going to be 110, right? So we have, so kind of our largest value would be something like this, and this would be the largest real number that we can represent that's not not infinity. Okay, so let's actually explore that just a tiny bit in our mini float representation, right? Okay, so with our mini float, this is the largest possible value we can represent. Okay, so what is this? This is going to be 1.1111 times 2 to the 110. 110 is equal to 6. No, yeah, is equal to 6, right? Minus our bias of 3. So this is 3. So this is 2 to the third here. Okay. So here I have 1 plus 0.5 plus a quarter plus an eighth plus a 16th times 2 to the third, which is times 8. Okay, and so here I have 1 and 15/16 times 8, and this gives me 15.5. So with my mini float, this is the largest value I can represent. Anything bigger than this will return positive infinity. Okay. Okay, and similarly, we can think about for double precision, we would have 0, and then we have 11 bits. 11 bits that would go 1, 1, 1, 1, 1, 0, and then we have 52 bits for the mantissa, and these are all going to be 1s. Okay, and that would be the largest that we can get in this scenario. Okay, and we can actually find this by typing in .machine, because these are inherent to our computer's processor, right? and this would be dot machine double xmax. Okay, this is the largest value that we can store with with double. Okay, so dot machine double. This is the largest value we can get. All right, and again, because we're using just a finite number of bits, so with double precision, I think we have 64 bits. We only have 2 to the 64 values that we can represent. Okay, or in this case, with 8 bits, there's only 2 to the 8. That's the most we can represent, and it's actually going to be less than that because of the way you know, the positive and negative infinity stuff work. Okay, so you know, we can only, because we're using only a finite number of bits, we can represent only a finite number of values. Okay, and at a certain point, you know, the numbers will just kind of merge into each other. Okay, and kind of the number line representation, if this is 0, okay, we have a lot of numbers that we can represent here. Okay, but then as things go on, the values we can represent get farther and farther apart. Okay, and we can represent lots of numbers near 0, but then as we get farther away from 0, they get farther spaced apart. And so pretty much, you know, this number and this number will, you know, these two values will just be represented as the same. Okay, we just don't have the ability to kind of distinguish between kind of those numbers, right? So, you know, earlier we had 15.5 was 110, 1111, okay? And this was equal to 15.5. And if I had this 110, 1111, I think this is, I'm sorry, I think this is 15. All right, let me just do the 8. This is, I'm subtracting off 1, 4, 8, 16, yeah. Okay, and so if you wanted to represent something like 15.3 or 15.4, you don't have that ability, okay? This is all we have, okay? So we cannot represent (15.3) or 15.2 or anything between 15 and 15.5. We just have to kind of pick one, okay? And the computer kind of has its own method for, you know, assigning. It's basically rounding. It's just saying, like, kind of figure out which one's closer, and it puts it towards there. It's a little bit more complex using the kind of the bit adder in there, but these two things would, you know, well, 15.3 would probably get sent to 15.5, you know, 15.35 would also be sent to 15.5, and 15.2 will probably get sent to 15. Okay, we don't have the ability to distinguish between these things. Okay, and that's just because this is the maximum amount of precision. We're only using 4 bits to store the mantissa. Okay, in double precision we have 52 bits to store the mantissa, which is a lot. Okay, but it's probably about 16 decimal places behind the 0, okay, in scientific notation, right? So if you've got a really big number and, you know, on the orders of magnitude of like 10 to the 100 or something like that, you know, you can only keep track up to about 16 decimal places behind the 0. And if you want anything more than that, the computer can't track that. Okay. I think some languages implement, you know, what's called a long. So double precision, you know, we have 52 bits, and if you need even more precision, not R, but other languages like Java or whatever, you know, they have a long precision which uses even more bits to store these things. But there's, at the fundamental level, we cannot keep track of an infinite number of decimal places. Okay, so so anyway, this is kind of the thing that we have, and that's what's going on. Okay, and then sorry, I'm like taking forever on this one topic here. There's also, we have denormalized numbers, okay? And this allows us, because if we think of kind of what's considered the smallest normalized value, okay? So the idea of normalized values in float have, you know, assume that the number in front of the one, or in front of the dot, is a 1. Okay. So you know, if we talk about if we have our established rules, okay, with the kind of established rules, if I have, I'm just going to write, what would this become? This is technically 1.000 times 2 to the negative 3, right? And this is technically equal to 0.125, right? And this means that there's actually no way to represent the value 0, okay? Okay, and so what we do is we introduce kind of some denormalized numbers, non-normalized, okay? So so if all the exponent bits are 0, we have denormalized values. Okay, and we will no longer assume that the leading number is a 1. Okay. Okay, and so instead, so 0, 0, 0, 0, 0.0000 will now become positive 0.0000 times 2 to the 1 minus 3, and this will become 0. Okay, and so now when you have denormalized values, the exponent is now 1 minus the bias, rather than just the exponent minus the bias. Okay, so rather than doing 0, 0, 0 minus the bias, it's now going to be, whenever you have all zeros in the exponent will be 1 minus the bias. So in this case, it will always be 2 to the negative 2. Okay, and so with denormalized values, the smallest value we can represent is going to be the following. Okay. Or the smallest non-zero value we can represent is going to be 0, 0, 0, 0, 0, 0, 0, 1. Okay. And so this is 0.0001 times 2 to the 1 minus 3, or negative 2. Okay. So this is equal to 1, 2, 3, 4. 2 to the negative 4 times 2 to the negative 2, or 2 to the negative 6, which is about 0.015625. Okay. All right, and then you can represent other really small values just using the same scheme. This would be 2 to the negative 3 times 2 to the negative 2. And so on and so forth. Okay. This thing this is our smallest non-zero value. Okay, and this is kind of the idea of like a machine epsilon. Okay. The largest denormalized value is going to be equal to what is this? 0.1111 times 2 to the negative 2, and this becomes 0.234375. Okay, and as soon as we get to the next position, okay, so now kind of the next value will be normalized. Okay. And that would be this is 1.0000 times 2 to the this is 1 minus 3, negative 2, and now we have 0.25. Okay, and so now we're in the normalized range. And what we'll end up noticing is that as we keep climbing and counting through this, the the gaps between kind of the values that we can differentiate will get bigger and bigger, because again, we only have basically 4 bits to keep track, okay? And so right now we can keep track of basically differences of 2 to the negative 6, okay? Because we've got this part is at 2 to the negative 2, and then this part, we're at 4 bits behind, so we can keep track of differences of 2 to the negative 6. But at a certain point, you know, as soon as these things get bigger, then we're only going to be able to keep track of differences of 2 to the negative 5 until at the very end, when we were at, oops, at the very end, when we had this kind of maxed out, the differences that we were able to keep track of was only 2 to the negative 1, okay? And so the same kind of phenomenon appears when we're dealing with, you know, double precision floating point, is that we can only keep track of differences of, you know, basically those 52 bits, okay? So 2 to the negative 52 times, you know, whatever's in your exponent. So, you know, pretty small differences, but non-zero differences, okay? And so let me kind of just flip back into our slide over here, and I just wanted to show you kind of what happens, right? So with integers, okay, if I raise 2 to the negative 1074 and I ask, is that equal to 0? It's going to say false. Or not integers, with double precision. So this is kind of the smallest that it can keep track of. And then if we raise 2 to the negative 1075, if I take whatever value this was, and if I were to divide that by 2, then it becomes 0 in terms of the math, okay? So obviously in real numbers, this is not equal to 0. But as far as the computer is concerned, it is no longer able to distinguish this value from 0, okay? So this is kind of the smallest it can keep track of that's not 0. And if, you know, if we did that, and if we said, you know, what is 1 minus this really small value, it says that's infinity, okay? Obviously that's not the case, but that's what it's resulting in, okay? If I take these large values, 10 to the 23rd plus 2 to the 1023 plus 2 to the 1022 plus 2 to the 1021, it gives me a very big value. This is approaching the largest value that it can kind of keep track of. If instead of adding 10 to the 21, but I add another 10 to the 22, the computer overflows and says that's infinity, okay? So this is called an overflow error, where it's no longer able to keep track of how big this number is. It maxes it out. That's an overflow. And then when it's no longer able to distinguish it from 0, that's called an underflow, okay? So this is an underflow. So here, this is kind of, we're approaching the smallest value it can keep track of. And here we get an underflow, where it says it's now 0. And over here, we get an overflow. Okay, and you know, we can ask, you know, what is 1 plus 2 to the negative 52? Okay, and we say that's x, and we're going to do x is what is this number minus 1, and it says, okay, I have this very small number around you know, 10 to the negative 16. Okay, if I say what is 1 plus 2 to the negative 2 to the negative 53, and we add that to 1, and I store that as y, and then I say what is y minus 1, it says the difference there is 0, okay? So, you know, in real math, this should not be 0, but for floating point it is, okay? So these are things we have to understand about the limitations of the computer. We can't expect it to be able to keep track of these small, tiny differences. And that this is just an inherent problem of using a finite number of bits, ones and zeros, to do it. Okay. You can read more about all of this in kind of the Wikipedia article on how this goes. Okay, and then let's see. Okay, so when you do arithmetic, okay, on the computer, again, it can only keep track of a finite number of positions, and at the beginning, we saw something kind of like this, right? We said this was a toy example, but the idea was, when you did some arithmetic, you might not have gotten results that you expected, right? So we say, what's plus 0.1 plus 0.2? The answer to that's 0.3, okay? And then we can ask, is 0.1 plus 0.2, is that equal to 0.3? And if you do this right now, even if I put this in parentheses, 0.1 plus 0.2, and I say, is that equal to 0.3, it's probably going to return false, okay? And this might be surprising to you. You might say, can I even trust the computer anymore? Yeah, the problem is when 0.1, when it's stored in binary, is not exactly 0.1. It's something very close to 0.1, but it's not exactly that, okay? And when we do 0.2 in binary, it's something close to 0.2, but it's not exactly 0.2. And when we add those things together, it is different enough from the computer representation of 0.3 for it to register and say that that result is false, okay? So, what do we do? Okay, we say, well, what's the difference between this? Well, it's a small number, okay? That's for certain, but it's not zero, okay? And so there's a function called all equal, okay? And this asks if two things are equal within a certain tolerance, okay? And kind of this machine epsilon, they ask if it's a certain tolerance. Now, this is useful, okay? But don't try to prove mathematical results using all equal or something like that, okay? Because this is just asking, are two quantities similar enough within kind of the machine precision levels? And that's what it returns. And if you want to know, like, does this one line and do these two functions equal at a certain amount, it might not be able to prove that, okay? We can get to within certain precision, but you can't then say, like, oh, well, the computer found a solution, so therefore it means these things are equal in math, okay? So so this, in this case, all equal is something, gives us a result that we would expect, but if I asked the computer, you could imagine a different scenario where I said, is 15.3 equal to 15.35, okay? In a scenario like this, using all equal would return true, okay? Even though in real life these are not equal, okay? The equivalent using double precision, okay? So there, all equal is a useful function. That's for certain, but there are limitations to what it can do. Okay. Loss of significance. This is kind of another issue that we have to worry about a little bit. So, let's say we tried to keep things with 20 decimal places of precision. Oh man, I got to get at it. Hurry up, because I have stuff to talk about. Okay, and we can store this into the computer, and we get something that looks a lot similar, okay? And if I said, okay, well, what is this? 1, 2, 3, 4, 5, okay, all the way up to here minus this number. And it tells me, okay, the difference there is all these zeros, 7, 8, 9, 0, okay? And this would be, 7.89 times 10 to the negative 16, okay? And that's, the computer can do this, okay? So this is what it should be in real life, right? In real life, it should be this. However, if I ask the computer, so these are not computer answers. These are answers that I wrote out myself, okay? And the computer, this is something you can tell the computer did this because it returns the symbol that this is a computer calculation, okay? When we do this on the computer, however, the exact computation that I have, it's not, because things get lost a little bit in here, it returns a number that's fairly significantly different from the true answer. Okay, so here I've got 7.89 times 10 to the negative 16. The computer is able to accurately represent this number itself, but it's not able to accurately do the calculation to get that number. Okay, because when it stores this number, some of that information is lost, and when we try to get the difference between them, we lose that, and we get something that's not quite right. And these kinds of errors, if we went on about our lives as if this was the true answer, and then we multiplied it at something, we could run into some problems here. Okay, I'm going to just skip all this stuff on computational time in memory. Okay, not that big of a deal. Okay, let's talk about root finding. All right, so all of this stuff with all of this floating point arithmetic, all to say the numeric methods that we will look at have its limitations. Okay, and so we can't represent real numbers completely accurately on the computer. We can just we're dealing with a set level of precision. Okay. Root finding. We are looking at some numeric methods now. Okay. The whole idea behind numeric methods is we have some kind of problem that we are trying to solve, and we just need to get an answer that's pretty close to the true answer. Okay, we like within a few like several I don't know, 10 to the negative 6. Okay, some level of precision that you want. We don't need the actual analytic answer. Okay, it's kind of like, do we need to know the true value of pi to 1 billion decimal places? Probably not. Okay, we can do engineering and do good work using an approximation of pi. And so numeric methods for root finding, we're not going to get the exact thing. We're going to get something that's pretty close. And pretty close is pretty close, like off by 1/1,000,000th of a thing. Okay. Sometimes we have equations that we want to solve. Okay, and maybe they are too hard to solve algebraically or with the tools that the mathematical tools that we have. Okay, and so here I'm working out of the Spurs text. Okay, this is like scientific programming using R or something like that. And they have an example 10.1.1, okay, is on loan repayments. And they have this equation. They basically say, okay, you know, try to solve you don't have to copy this down, okay? I mean, you can. All right, and you want to solve for R given n. I'm sorry, A, P, and N. And it's hard, okay? This is hard. Okay, so one option that we can do is we're going to we write the function f of x, and all we do is we just say we're going to subtract AP from both sides, okay? Or this thing from both sides, okay? And we have A over P minus, and then because now we're solving for x, R, okay? And then if we find where f of x is equal to 0, you know, these are solutions for the value of R. Okay, so we can reframe difficult equations to solve into a root finding problem, okay? Because again, root finding is where, you know, finding locations where a function is equal to 0. And you probably covered some of these things in like your calculus class, some numeric methods and things like that, okay? And so you can read through the examples, and I'll just kind of, we'll start off with some simple ones, okay? I'm going to do cover some of these methods a little bit out of order, but you know, I think they make sense. Okay, so so let's say we have some function f of x, okay? And this is our x-axis. This is where y equals to 0, right? And then you just have something like this, right? We want to find this root. Okay. All right. So the first one that we'll cover is the bisection method. And this is easy. All you have to do is you just pick two boundary locations. Okay. You have basically an x left bound and an x right bound. Okay. Okay. And the only requirement is that f of x on the left must have the opposite sign of x on the right, okay? Which is the case. Yeah, here I'm negative, here I'm positive, and because of math, we know that it has to cross the x-axis, right? Unless it's disjoint. I guess prerequisite 0 is that the function is continuous. Okay. All right, so we do this, okay, and then if they have different signs, all you do is you find the midpoint Okay, so then calculate xm, which will be the average of these two. Okay, and then pick xm, and you're going to use xm in either xr or xl, but you're going to use the one that has a different sign from xn. Okay, so find the sign of f of xm. Okay, and then keep either f of xl or f of xr that has the opposite sign of the midpoint. Okay, and then you just repeat this process. So if we start here, then so after one iteration, this becomes the new x left. So let me okay, so we start here. So this will be iteration 1. Okay, so we calculate this. This becomes the new XL. X left, and then we keep this. All right, okay, and then so now I have this, and then we just do the same thing again. Okay, iteration 2. Here we'll blow this up a tiny bit. Let's erase this. Okay, and then so we find the midpoint of these two spots. Okay, and then so we calculate the sign here. So this is XL, X right. This is the new midpoint. Okay, and then so we will keep this, and we keep this one now. Okay, and then now we have this position right here. And then we just keep bisecting over and over and over. And then, I don't know. It looks like it's going to be pretty close, okay? But, you know, one of these will be positive and one of these will be negative, okay? Unless you get exactly where it's 0, and then you have succeeded, right? But chances are one will be a little bit larger and one will be a little bit smaller, okay? So, you know, XM, XL, XR. Okay, and then so we will keep this and this, and further zoom in, okay, until we get exactly where it is that we want. Okay, and we just keep zooming in closer and closer and closer, all right? And just repeats until basically the difference between, or actually the difference between XR and XL is less than some epsilon. Okay. So you just keep repeating this until it gets to a certain tolerance, and then you're happy with the location that it has found. Okay, and then probably pick basically xm equal to your final as your kind of root. That's the bisection method. The great thing about the bisection method is that it's guaranteed to work. Okay, as long as it's a continuous function and you start off with that the rule that one is negative and one is positive, and it crosses through, it's definitely going to succeed in finding a root. The disadvantage is that it's one of the slower methods. Okay, it requires a lot of iterations to kind of get to the a certain spot. Okay, so the bisection method will almost always work. I'll say no. Will work. Okay, but a little slow. Maybe it takes a bunch of iterations to get there. Let's see. Do you want me to code that up right now, or do you guys feel like you could code it up yourself? Okay. Well, we'll see here. Let me talk about the Newton-Raphson method. Okay, Newton-Raphson and secant method. These are highly related, and there'll be exercises in your homework that deal with these things. Okay, so let's here we'll do the secant method. Okay. All right, so the idea here with the secant method is you've got some kind of, let's see, some kind of function, right? And you just pick 2 points. It doesn't even matter where, but let's say these are your 2 points here. And we'll say this will be xn plus 1, okay? And you connect these 2 points with what we call a secant line. How do I do this? Okay, so this is your secant line. And then you find where this secant line crosses 0. Okay, and this is going to be I'm sorry, I've labeled these incorrectly. This is technically xn at time n minus 1. Okay. So you have this spot, you connect these two with a secant line. Okay, and it's easy to find where the secant line crosses 0, right? Okay, and so where the secant line crosses 0, this is going to be the next point, xn plus 1. This is where secant crosses 0. Okay, and then you say, okay, what is the function at that point, xn plus 1? okay? And this becomes the new location, right? And so now at the next iteration, let's see. So now we have xn, and this is the new spot. Oops, I have to. This crosses right here. Okay. And this becomes the next spot, all right? And you get a little bit closer, and now you have another location, okay? And then now we use these two, and perhaps we will, maybe this is getting me a tiny bit farther away, but we'll get there. So here I have this spot and this spot. I don't know if you guys can see that, okay? And so now these cross these two dots. Let's see. Okay, and so we can see that this line is even closer to where the function itself crosses 0. Okay. So this is technically x at n plus 2, and this spot right here is going to be x at n plus 3. Okay. With each iteration, we establish a new secant line. We find where that secant line crosses 0. We use that, and then the last point, and we keep crossing, and we keep doing that until we get closer and closer and closer to where the function crosses 0 itself. Okay. Okay, so the secant line, kind of the method is start with 2 points, and they don't even have to be on opposite sides. Okay. Start with 2 points, ideally relatively close. This is relatively close to the root. Okay. Find the secant line that connects those 2 points. Okay. Find where the line crosses 0. Okay, to establish a new secant location, secant point location. And then you just keep doing that over and over and over, repeat until the differences between new points approaches 0, okay? And that's the secant method. I feel like I should way to no. I don't know if there's a way to make this better. I want to give you guys a better picture. Okay, so here and here, we'll connect these two. Just pick any 2 spots. So this will be xn minus 1, and this will be my new one, xn. And you just connect those 2. Okay. Okay, and then once you have that, then let me see if I can erase this line. This is just used to determine the new location. So right here, we get another line here. Two. Sorry, the details get lost in my little diagrams here. But you know, we're just zooming in closer and closer to this spot. Okay. So this is X. This is now going to be, this becomes xn minus 1. This is the new xn. This spot is now irrelevant. Okay. And then once we have that, for the next iteration, we're going to zoom in on this location right here with this spot and this spot right here where it crosses. We zoom in right here. Okay, and we just get closer and closer and closer to where it actually crosses the 0 point. So this is the actual root. We're going to use this location on this spot right here, and we'll use this location right here. We zoom in even closer, and I mean, right here, the difference between the actual root and where our secant is probably, you know, too small for us to really appreciate. And this is how it works. Okay, it works rather quickly. The location that it gets to gets very close to the actual root itself. Okay, and so this is now xn minus 1. This spot is xn, and then this is our new location, xn plus 1. Okay, and we can see xn plus 1 within a few iterations. Xn plus 1 is very close to the actual root. Okay, that's the secant method, and then the last one is Newton-Raphson method, which you probably covered in your calculus class, I imagine. The idea here is rather than using secant lines, you're using tangent lines. Okay, so if we have some function here, and let's say we've got, okay, we have something. You just pick a location right here. You've got xn, x of n, and then what you do is the Newton's method requires that you find the derivative at x sub n. Okay, so we have so we need the tangent line at f of xn. Okay, and so you know that requires a differentiable function. Okay, and so anyway, we find the tangent line to the thing right here. So whatever this looks like. So is that tangent? Maybe. Okay. So we find the tangent line, and where the tangent line crosses 0, that's going to be our next point. So this is going to be xn plus 1, and then we zoom in right here. Okay, and we say, okay, starting at this point, let's go up to the line here, and we're going to find the tangent line at this point. Okay, so we go, okay, right here. Let's make this tangent right there. And we can see how quickly this might converge. So tangent at this line gets us to right here. Okay, so this is, you know, for this iteration, this is xn, and this is going to be xn plus 1 right here. Okay, and then we can just keep zooming in and in and in, and we'll eventually get even closer. Okay, so we need the tangent line at f of x. Okay, and then we find, so sorry, this is the Newton-Raphson method. Okay, we find where the tangent line crosses 0. Okay, and we use that location as our new x of n. Okay, and then we repeat the process. We find the tangent line at f of x of n, find where that line crosses 0, and we repeat that. Okay, and you know, finding where this is going to cross, the relationship between x of n, the location of x of n, and x of n plus 1 is not too bad. Okay, if we think about, you know, what the definition of the slope is. Okay, this is if this is the run and this is the rise. Okay, the, you know, x of n plus 1 is going to be equal to x of n minus the run, right? Okay, and then what is our slope? Slope is equal to rise over run. So we can find the run as rise divided by the slope. Okay, and then so that just gives us x of n plus 1 is equal to x of n minus the rise divided by the slope, which is going to be f of x of n divided by f prime of x of n. Okay, and this is how we get our next iterations. So I mean, you can, I mean, it looks nice to draw the tangent lines and follow it, but technically, with Newton's method, all you have to do is you just say, okay, if I'm here at x of n and I just want to subtract off the length of this segment here, which is my run, I can just use the definitions of what slope and run and all of that is, and we say the run is rise divided by the slope, which is going to be f of x divided by f prime of x. Okay, and this will give us the new location here. And we just repeat that over and over and over until a point where the difference between the last value of x of n and the next value gets smaller than a certain level of tolerance, maybe like 1 in 100,000 or something like that. And we accept that, and we'll say this is the value of the root. Okay? All right. We'll end here for today, and we'll see you guys on Thursday.